Wasn't the timer? Which one? Can I one what?
It's a question
Number one. See this one. This they are party of this survey. They are a survey. So this is strata. Sorry.
No, there are 4 people.
There are 4 people.
That's their weight. It's like I was saying in class. Like,
Oh, this is for people like Harry,
yeah, so,
Brady,
yeah,
blah, blah.
those are people.
And another represents household maybe.
Well, they represent the population. That's what I'm saying. There's 4,000 other people in the population like this person. That's what the weight is.
So this one.
That's their household weight. So that's part of the overall selection of that person, because their household was sampled. But then they were sampled from within that household. That's those additional pieces of selection.
Oh, and what is this?
That's the oversampling, right? So African Americans were sampled at a rate twice as high as non-Africans.
So this means one is like
they get a lower weight than the people who were undersampled, right? The probability of being sampled within the household was half for these people of what it was for these people. Hence, when you invert that, you get a 1 and 2.
Oh, this one of a 2.
Yeah, that's this piece. That's the probability. There were 2 people in that household. 1 person was selected, so that was their probability of selection given how many eligible people are in the household.
Oh,
but there were oversampled.
Oh.
These guys were oversampled, so they had a higher probability of selection than these guys. So these guys needed bigger weight. These are weights.
So two house, 2 persons.
2 people were eligible within that household.
So the probability of selection of the household.
That's, and then they're oversampling, and then
and this is oversample like addition of one.
No. It's a weight. Remember, it's an inverse of a probability of selection. The probability of selection for these folks within a household is half of the probability for these folks. African Americans were oversampled.
I get that, but I want
that's just a weight.
Oh.
These people get twice the weight for the oversampling as the African Americans.
I will think about it.
Okay, so this one unified by this one will be half.
That's eligible. See, this is a weight for the eligible selection. 1 out of 2 were selected, hence the weight is 2. Probability of selection was 1/2, but there was no oversampling. These folks were oversampled, so they only get a weight of 1. These folks have to get weighted up because they were undersampled by design. These are all weighting adjustments leading to that final piece. We got to get started here. Yeah, so just study that a little bit. Those are all weights. That's the thing. Those are all weights. Okay, let's go ahead and get started again. All right, so now we're turning to module 3, which has to do with sampling error calculation models. So this is essential information to lead into our discussion of variance estimation next week. So some of you have started to ask questions about how to actually calculate variance. To get to that point, we have to understand where the stratum codes and the cluster codes come from in the data sets that enable us to estimate variance in the first place. Okay, so this piece, this short little module here, is about where those codes come from that we see in the data set alongside the weights that allow us to estimate variances. Okay, and that's what we call a sampling error calculation model. Okay, so just to step back a little bit in the class, so far we've talked about the basic concepts of complex sample designs, the notion of design-based inference, and design effects, and the components of the design effects. And today we talked about survey weighting, The idea that we have this product of selection weights, non-response adjustment, and then post-stratification or some more general form of calibration. That gets us to our weights. But now we need to calculate those standard errors to form our confidence intervals, to test hypotheses. And to do that, the data user needs to see variables in the data set that reflect the complex sample design information, in addition to those final weights that we just talked about, okay? So that's where we're headed here to talk about variance estimation. And we'll see all these formulas that talk about the reduced degrees of freedom. We're gonna go over the formulas that are used to calculate variance in stratified cluster samples. So we're gonna see all that, we're just not there quite yet. Okay, so with sampling error calculation models, it's always best to start from an example because you're gonna see a different sampling error calculation model for every single survey. Okay, so it's best to start with a single survey and think about what was done there, and then we can think about the ideas more generally, okay? So the idea of a sampling error calculation model is you're giving the data user the best possible approximation to the original sample design. You're not providing the original sample design straight on PSUs and all that kind of good stuff, usually because you're trying to minimize disclosure risk. You don't want to provide that original identifying information for all the characteristics of the sample design. Furthermore, you want to provide design information that's immediately compatible with the various computational methods for variance estimation that are implemented in the software that we're going to be talking about. Okay, so the variables provided need to be in alignment with what the software procedures are going to be looking for to enable variance estimation. Okay, so if we look at the National Comorbidity Survey, we have to make this distinction between the original probability sample design and the features of that design, and then what's actually provided in the data set for sampling error calculations. Okay, that's the mapping here. Okay, so the original design for the NCS was a stratified, multi-stage design that only took one PSU per stratum, and those PSUs were sampled without replacement. Okay, now that original design is not immediately compatible with computational methods. Why? First of all, only having one PSU per stratum, we can't estimate between cluster variance within a stratum. There's only one PSU. So that's fine for the sampling, but we can't calculate the contributions of each stratum to the overall sampling variance with only one PSU per stratum. Second of all, those PSUs were sampled without replacement. Okay? In that kind of sample design, the data user would need a whole bunch of additional information about joint probabilities of selection of the PSUs to calculate variance estimates. And no data producer wants to provide that giant matrix of joint selection probabilities. You think weights are complicated. Looking at a matrix of joint selection probabilities, nobody's going to want to deal with that for analysis. So while it's a perfectly fine, valid probability sample design, it's not ready for actual computation. Okay? That's where the sampling error calculation model comes in. So in that sampling error calculation model, we still retain the essential stratification. We form what are called ultimate clusters that summarize the multi-stage process. We're going to talk about that, but basically that multi-stage sampling process results in one cluster of observations from a given PSU. We either combine or collapse these original PSUs to form two ultimate clusters per stratum. And now we have two pieces of information per stratum that allows us to calculate a variance contribution. We need at least two from clusters from a given stratum to estimate variance. And we assume that those ultimate clusters were sampled with replacement as opposed to without, which allows us to avoid those joint selection probabilities. So these are all approximations. This information does not immediately reflect the original sample design, but it comes very close and it enables data users to estimate variance. That's the idea of the sampling error calculation model. We're going to go into this in more detail. Now, what does this mean for our standard errors? Because we're making all these approximations. When we use the different variance estimation techniques that we'll be talking about, like linearization, replication techniques, under these approximate sampling error models, the standard errors are going to tend to be overestimates. variance of the true sampling variance that was associated with this original design. And we're okay with that because it makes our inferences conservative. Okay, we're not shrinking our standard errors. We're not calculating smaller p-values. We're allowing people to estimate variance, allowing for a slight amount of overestimation in the variance, making our inference more conservative. Confidence intervals wider, standard error is a little bit higher, p-value is a little bit higher. We're just being more conservative in general. Okay. So we're going to keep going into these concrete ideas. So the idea of an ultimate cluster. Suppose you have a multi-stage design. PSUs, like that 3D picture that we showed, PSUs, SSUs, households, people. The idea of an ultimate cluster is that within a given PSU, this multi-stage sampling process ultimately yields 4 respondents from that one PSU. We think of this collection of 4 respondents as being the ultimate cluster that emerged from that PSU across the entire multi-stage process. So that collection of respondents within the PSU, that's what we refer to as the ultimate cluster. Very simply put, it's just a collection of respondents in that PSU. We refer to that as an ultimate cluster. Now, there could have been many possible ultimate clusters of size 4 coming from this PSU. This is just one possibility. You can go through the whole thought exercise. It could have been this person, this person, this person, and this person in the multi-stage design. You could write down all the possible ultimate clusters that could have come from that PSU. The thinking is we take a width replacement sample of these ultimate clusters and we take all 4 from that ultimate cluster. So we're pretending that it wasn't really a multi-stage design. We're saying there was just a sampling of a cluster. We took all 4 people within that cluster. Okay. We could have taken a different cluster of size 4, but that collection of 4 people is what we use as a variance estimation cluster, an ultimate cluster. Okay. We just care about what comes from that one PSU. That's it. So we're ignoring those other stages of the sample design. Granted, there's sampling variability at each of these stages, but the contributions of the sampling variability at the lower stages of sampling are absolutely dwarfed by the between PSU variance. That variability between the PSUs and these ultimate clusters is what defines 99% of the sampling variance, okay? Not what happens at lower stages. So when data users see these data sets, they essentially see some approximation of the clusters defined by the PSUs, and that's it. That's why we only care about that first stage of sampling in this case. All right, so we work with those ultimate clusters for variance estimation. The idea is that one ultimate cluster is selected from each PSU. There could have been many, but we assume that those ultimate clusters are sampled with replacement. We consider those ultimate clusters then for variance estimation. So the assumption that we're making is we have a single stage with replacement selection of these ultimate clusters, and we take every element from within that one ultimate cluster, all 4. Okay? It's the same essential information, but it's just a different assumption that we make to allow for variance estimation. Okay? Rather than worrying about the multiple stages and so forth. Everything's kind of rolled up. Now, these are assumptions. They greatly simplify the formulas that we ultimately use for variance estimation. They make computation more straightforward, which is part of the whole idea. But Kish, all the way back in the 1960s, said, this isn't perfect. This is an approximation. It allows us to perform computation. He showed mathematically the amount of overestimation that this would introduce. So you can actually look in his book in that section saying, this is how much higher the variances will be from making these assumptions relative to what they actually should have been. And that amount of overestimation that he shows, that's the beautiful thing about these assumptions. It seems like you're making a lot of big leaps to simplify things, but the net effect on your variance estimates is tiny. They're just slightly bigger than they should have been otherwise without making these assumptions. Okay, so it makes it very easy to do this kind of stuff in a computationally friendly way then when you make these assumptions about the original sample design. Okay, so in theory, again, you could enumerate all those possible ultimate clusters of a given size that could have been selected from a PSU, and we assume that they've been sampled with replacement. So the variance estimation procedures that we're going to be talking about are based on those ultimate clusters, and some sampling error calculation models, again, are either going to collapse or combine these clusters to result in these larger sampling error clusters, which we call C groups, or sampling error computation units. I'm going to show you some examples of that. And there's more detail about how these CQs get formed in section 4.3 of Applied Survey Data Analysis. Okay, we'll look at some examples here in a second. Okay, so one way that these sampling error calculation units and strata get formed is by this idea of collapsing strata. Okay? Again, this is all done after the fact. We had our sample design. Now we're trying to create stratum and cluster codes that the data user can work with for variance estimation. Generally, collapsing is done when there's one PSU sampled from each of your different strata, as was the case in the NCS design. They only took one PSU without replacement from each of the strata. Okay? Different places do this differently. Michigan tends to take one PSU from each stratum because that allows for very fine stratification of the sample. Okay? Just taking one PSU from each strata, you can define many strata, okay, to get your PSU. So, but other agencies may do it a little bit differently. The point is that if a stratum only gives you one PSU, you can't compute a variance. There's no between cluster variance within a stratum. So collapsing, basically you break down the barrier between adjacent strata or strata of similar size, and you form a larger pseudostratum with multiple PSUs. You collapse the boundary between strata. That gives you a bigger pseudostratum with multiple ultimate clusters for variance estimation. That's the whole idea here. But it doesn't come without a cost. When you collapse strata, it does introduce a positive bias in your variance. That again is that inflation and variance that comes from this approximation technique. And Kish generally suggested that you should collapse design strata that are similar in size, in population size, to minimize the amount of positive bias from this procedure. Okay? This is just a picture of how that looks. Suppose you have two strata in the original sample design. Each of the strata, you're just taking one PSU. So PSU A was sampled from stratum 1, PSU B was sampled from stratum 2. Again, other sample designs, they might take multiple PSUs from each stratum. That's fine. If you have a design like this, you're left with a problem for variance estimation. So the idea of collapsing, you simply break the barrier between these two strata and you form one larger stratum with two PSUs present. Okay? So we have fewer strata now in the data set, but at least we can estimate variances. And that's where we have some increase in our variance estimate. We just have fewer strata in the original design. Actually, we might divide it by 2, depending on how much collapsing we do. Okay?
We believe that some variables like names and GPS. It's still possible to identify the.
This again, you're not doing this as a data user. Okay, so we really have to set the stage. This is not something that you do in analysis. When data producers are preparing these stratum codes and cluster codes, this is something that's done before the data set ever gets released. This is not something that you're trying to figure out how to do as a data analyst. You're not going to have enough information to do this kind of collapsing. This is something that the data producer does.
Yes, that's what I'm saying. As a data producer, so that collapsing and avoid just some GPS and names. That there are some people.
I think you're making it too complicated. Like you're just literally saying, if this is stratum 1 and stratum 2 in the data set, I'm going to call this all stratum 1. That's all you're doing. There's nothing to do with GPS or addresses. You're just identifying two strata that are similar in some respect, and you're combining them into one bigger stratum. That's all you're doing. That larger pseudostratum is what you ultimately would release with the data set. That's all. And Kish's guidance will say you would collapse strata that are similar in population size. That's the guidance that he generally provided. Yep, that's
Yeah, great. I would like to talk about exactly this fact. You put together stratum that are similar.
right.
Okay. So we have to study before, analyze this stratum, and put it together.
Right. Yep, that's the idea. So literally, these were two strata in the original data. You're now forming a new stratum that you might call 994. You mask it, right? But it's the collapsing of the boundary between these two to form one larger pseudostratum. That's what would get released, not the original strata. And again, this is not something you do as an analyst. This is how the data producer is preparing the data set for you to work with. That's the key point. Okay. Now that's collapsing. Another thing that data producers might do is combining strata. It's similar in spirit. So this happens a lot when the sample design contains many strata and the data producer wants to simplify the stratum coding. They not have as many different strata for depending on what the analysis needs might be. This also happens when the data producer is worried about disclosure protection. So you have a large number of PSUs where the sample sizes are relatively small. And you want to combine the PSUs from different strata to create larger pseudo PSUs with more sample in each of them. Okay. Now, the nice thing about combining is it doesn't produce any bias in the variance estimates, like collapsing. Okay? It just reduces your degrees of freedom, right? You have fewer clusters to work with. Okay, so that's the loss, but it doesn't add any bias to the actual variance estimate. So this is a picture of what might be meant by combining, right? Similar in spirit to collapsing, but notice in the original sample design with 2 strata, there were 2 PSUs in each of the strata. I was fine. I could have stopped there. I could have released these codes to the public. They could estimate variance. Everything was fine. Okay. No need for anything else to be done. But the data producer was saying, well, the sample sizes in each of these PSUs are pretty small. And that makes it easier potentially for somebody to identify who the respondents are. Or if somebody's doing a subgroup analysis, maybe there are certain subgroups who won't be represented in one of these PSUs due to the small sample size. So I'm going to combine across these 2 strata so that I produce these larger pseudo clusters, which are called sampling error computation units, all coming from one pseudo stratum. Okay, so it's like collapsing, but you're also combining PSU information from across the different strata. Okay? So again, typically done to minimize disclosure risk and allow for more heterogeneity within these clusters for subgroup variance estimation. Okay. So another thing that might happen in the background is often with sample sizes in mind. And it doesn't, the nice thing about this particular technique is, again, it doesn't add bias to your variance estimate. So that random combining across different strata isn't going to add any bias to the overall variance estimate. You just have fewer clusters to work with, right? So we talked about degrees of freedom being a function of how many clusters you have. This is shrinking the number of clusters. So you lose degrees of freedom. Okay. Another technique that's used in the background to approximate the sample design is random groups. This can be done when the sample design strata contain many different PSUs and the data producer wants to simplify that cluster coding, okay? Create larger clusters or again, limit disclosure risk. Similar to combining strata the way that it's done, it's often used to build SICUs, these sampling error computation units, in what are called self-representing PSUs. Those are PSUs that have a probability of 1 of being included in a sample, like giant metropolitan areas like New York or Manhattan or Los Angeles or Chicago here in the United States. Within those self-representing PSUs, which will be included in every sample, you're again left in a situation where you just have 1 PSU in a stratum and you can't really estimate variance. So the units at later stages of the design, like area segments, they're randomly combined into groups that enable variance estimation within that 1 PSU, that self-representing PSU. So this random creation, again, of sampling error computation units that will enable variance estimation. Okay? Similar to combining, when you use the random groups method, you're not biasing your variance estimates. So this might be an example of random groups where in a given stratum that had 8 PSUs, again, no problem. Right? We can estimate variance based on these 8 PSUs. We could have released this to the public if we wanted to. But again, due to sample size issues or subgroup estimation, whatever the case may be, the ultimate clusters from these PSUs are combined at random into these larger groups. And that produces a stratum, same stratum as we had originally, but now that same stratum has 2 sampling error computation units. The bare minimum that we need for variance estimation, but it minimizes disclosure risk and it gives you bigger samples within each of the clusters. Okay, fewer degrees of freedom. Okay, that's another thing we're sacrificing, but meeting all those goals of the random grouping. Again, minimizing disclosure risk, bigger subgroup sample sizes. So you might also see this happen, and it's often done to create two SICUs within a stratum for the types of variance estimation techniques that we're going to be talking about. One technique called balanced repeated replication needs two clusters per stratum. So sometimes this is done to enable particular variance estimation techniques in the first place. Yep, Faisal.
But when you random the stratum, you lose the potential of putting together stratums that are similar.
Well, this is all happening within one stratum. This doesn't involve messing with the strata, this technique here. See, this is all happening within one stratum. I'm not collapsing I'm not collapsing. Yeah, this is just happening within one stratum. Yep. But the point I want to make is that if you were the data producer, you would be just fine releasing this, right? But if a data user wanted to do balanced repeated replication, which we'll talk about next week, this would not allow for it. So giving them two clusters within the stratum does allow for balanced repeated replication and meets all these other criteria. Yep. It's the homework is referring to whatever stratum variable is provided in your data set. So if the documentation for your data set says we started with stratification by region of the US or whatever, but then there was collapsing or combining or something like that, just briefly summarize that process. That's all. Yep. The message is that more often than not, the stratum codes and the cluster codes that you see in the data set are not the original stratum and cluster codes. They're approximations that were designed to allow you to estimate variance and to meet these other criteria, like I said, about sample size and subgroups and so forth. Okay, so this is a big table that kind of shows you what's going on in the background here with respect to applying these ideas. And this comes from the National Comorbidity Survey. So in the original design, the PSU column, these are all the original PSUs that were sampled. Okay, that's the first thing to note. So the PSU column, that's the original design. So take this first PSU, which hint, hint, is actually New York. These are meant to be masked so that people don't identify what these are. But we can say several years later, this is actually Manhattan. Okay. Within Manhattan, that PSU was divided into two strata. Okay, that's how big Manhattan is. There's like a north and a south stratum of that original PSU. Okay. And that was a certainty PSU. So Manhattan was included in the sample with probability 1. Okay. The actual random sampling within Manhattan did not start until the block segments were selected. That's really the first stage of sampling within these certainty PSUs because they appear in the sample every time. It's like an entire stratum. So this is the random stuff that actually happened. And following the random groups technique, these area segments were randomly grouped into these SICUs. Okay, so from that first stratum from New York, SICU 1 was area segments 4, 9, 14, 19, 25, and so forth at random. That was random grouping. SICU 2 within that first stratum was 1, 5, 10, 15, 20, 26, etc. So we went from one original certainty PSU to 2 design strata with 2 SICUs each based on the random grouping method. That's what the data user is going to see. They're going to see these 2 stratum codes, these 2 SICU codes for each respondent. They're not going to see this original PSU. Okay, and so forth and so on. All of these here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 16. These were all self-representing PSUs selected with probability 1. So they had SICUs formed, and they usually each formed their own stratum by the random grouping method. Okay. Now, when you came to the PSUs that were not self-representing, okay, selected with less than probability 1, the collapsing technique was used. Okay, so 17 was selected from a stratum, 18 was selected from a stratum. That was the only PSU sample. The boundary between these two strata was collapsed to form stratum number 20. And these were labeled as SEQs 1 and 2. There wasn't any kind of random grouping done because these were selected at random to begin with. The boundary was just collapsed to create these two SEQs here. And that's what the data user sees. So now the data user just sees these stratum and SEQ codes. They can't tell what was a certainty or a non-certainty PSU. They just see this stuff for the sake of variance estimation. And now every stratum has 2 clusters available for variance estimation. And they can use balanced repeated replication if they want. It opens the door for a variety of different variance estimation techniques. But we're still capturing the essential features of the sample design. Essentially the same stratification, more or less the same clusters as were originally selected. So it's not exactly equal to the original design, but it still is approximate. That's the idea. So the data user ultimately sees those stratum and SEQ codes moving forward for the sake of variance estimation. And slides 16 and 17 in module 3 just summarize everything I just described about the table. So you can refer back to that to see how this collapsing and combining and random grouping was done to ultimately create those sampling error codes in the first 2 columns. So these first 2 variables that you would see in the data set, that's what we would refer to as the sampling error calculation model. Those 2 variables. And those are the variables that you would input to the software for the sake of variance estimation. Okay? That's the way this is working. So you don't see the original design codes. You see these approximations that are compatible with what the software is looking for the sake of variance estimation. Okay? So if you look at the lab notes for today, which I'll turn to quickly here. So I have Stata open on the screen, and I copied the lab notes from today into this do file editor within Stata. This is where you can run Stata syntax. That's the basic idea, and we'll keep looking at this as we go. What I've done is I downloaded the NHANES data set from Canvas, and I saved it in the directory that you see here. Okay? So you can download the NHANES data set and put it wherever you want. That DTA version of that data set. I saved it in this particular directory so I can access it. So in Stata, I'm saying to change my directory to this location. And then I'm saying to use or open this particular data set from that location. That brings the NHANES data into Stata's working memory. Okay? So in the do file editor with the code that you see in the lab notes, if I run these 2 lines, in Stata then, that opens the NHANES data set, and I can see all the different variables in that data set up here in this variables window to the right within Stata. Okay? So what I want to show you is just a simple crosstab of these sampling error calculation model codes that were created for the NHANES. Okay? If you scroll through this list of variables, you see this variable called weight int for the medical history interview weight. You see this variable called weight MEC, that's for the exam weight for the NHANES. So 2 different weight variables. Right below that, and this is often the case in these data sets, you also see the sampling error codes for variance estimation. And that's what we need to make sure that we're accounting for when we calculate our standard errors. But these are the approximate codes that were created by the NHANES data producer to enable users to estimate variance. STMV-PSU stands for Standard Deviation Masked Variable PSU. It's an approximation of the original PSU code for the NHANES, enabling estimation of the standard deviation of the sampling distribution. That's the whole thing in a nutshell. Next up, you see the stratum codes. Okay? So those are the 2 variables that we would need to input to the software to estimate variance. If I just look at a crosstab of SDMV strata with SDMV PSU, okay, that gives me a flavor of the sampling error calculation model. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 strata according to the sampling error calculation model. Maybe the original NHANES design had 20 strata. Some were collapsed, some were combined, but approximation of the original stratification. And within each of those strata, I see these pseudo clusters, these ultimate clusters that may have been combined or collapsed. Some of the strata have 3. Some of the strata have 2 for the sake of variance estimation, but they all have at least 2 to allow for variance estimation within each of the different strata. Okay? So then, just to kind of foreshadow what goes on in the rest of the lab notes, since I know we're over noon here, what we do to set up this kind of design adjusted analysis that fully accounts for the weights and these design codes when the standard errors are being calculated, all the design effects that we've been talking about thus far. Okay, we use a command in Stata called survey set, and that declares these design features to Stata globally, so that subsequent analysis commands refer back to these design variables for the sake of design-based estimation. The first variable that we list in survey set is our cluster code. In this case, it's SDMVPSU. Okay, so that declares what variable in the data set contains my cluster codes according to the sampling error calculation model. Okay, step 1. Second piece in square brackets, we identify our final survey weight. And if we want to do an analysis of a medical examination variable, I would use WTMEC 2-year. Okay, that's the weight I want to declare. We do that in square brackets. And this is all in the lab notes. I'm just typing it from scratch here. Okay. So clusters, weights, what are we missing? The design effects. Stratification, right? So many people, when they're doing these kinds of analyses, just do this. As long as I specify those weights, I'm good. That's not it. That's the key message. We have, for variance estimation purposes, have to declare the clusters, the weights, and the stratum codes. So we get that G in terms of the design effects, the gains and precision. So we do that after a comma, we say strata, and then in parentheses, the name of that variable containing the cluster or the stratum codes, which is this one in this case. All right. So when I run this command in Stata, that globally declares all of these essential design features for the sake of design-based analyses. I only have to do that once within Stata, and R is the same way too. Okay. Now that I have those variables globally declared, all I have to do for the rest of my analyses is start my favorite Stata command with SVY. So if my goal is to say calculate the mean of systolic blood pressure, BPX SY1, collected in the medical examination, I need that medical exam weight. If I want to estimate the population mean of systolic blood pressure, but I want to do it using the weights, and I want to make sure that my standard errors reflect the cluster sampling, the weighting, and the stratification, all I have to do as an analyst is just add SVY colon to that command, and I'm done. All the stuff we've been talking about in the class. Okay, submit that command. I get my weighted point estimate of that mean. Okay, and I get what's called a linearized standard error of that mean. We're going to talk about Taylor series linearization next week, but in the output, it's still crunching a little bit here, but in the output, it tells you how many strata were in the sampling error calculation model, how many clusters, ultimate clusters were in that sampling error calculation model, how many degrees of freedom do I have for variance estimation? Remember, it was clusters minus strata, 17. Okay, that's my degrees of freedom. The estimated size of my population based on the sum of the weights. Okay, and then I see my weighted, unbiased point estimate of that mean, 119.53, and its linearized design adjusted standard error, and that 95% confidence interval we've been talking about based on the right critical t-value, based on the right standard error. So all you have to do as a secondary analyst to set this kind of stuff up is declare those design variables and then modify your favorite command with SVY to implement the design-based approach in Stata. It is mindlessly simple. And that's one of the reasons, the fact that Stata has adapted this to so many different commands, that's one of the reasons people like using Stata so much for these analyses.
How do you output the coefficient of variation?
We'll go over a lot more of this. This is just a little example, but like if you wanted to calculate, the coefficient of variation of the weights, for example, you could say summarize, and then WT MEC 2-year, and you have to add a detail option to do that. And that will give you the standard deviation of the weights and the mean of the weights. So remember, the calculation was the standard deviation divided by the mean squared, right? So if I take, instead you can say display for this kind of calculation, if I just take roughly 35.2 divided by 31.4, and then I square that quantity, and I add 1, right? Coefficient variation squared plus 1, that was the formula we talked about. There's my variance inflation due to the variability in the NHANES weights, upper bound. So at a maximum, anytime I'm computing a weighted estimate, the weighting alone in NHANES is going to inflate my variance by about 2.26 as an upper bound. That's ignoring the cluster sampling, right? That's just the weighting. So one of the cool things Stata can do, and this is in the lab notes as well, after running that mean analysis, I can use what's called a post-estimation command called estat effects. That will give me the design effect associated with that analysis, the estimated design effect. There, the design effect is 2.574. So the vast majority of that design effect is coming from the variability of the weights in terms of that variance inflation. So that particular estimate of the mean, we see that the design effect on the standard errors is 2.574. Look at the ratio of the variances, 6.62. So just this one estimate alone, the complex sampling features of the NHANES, all three that we specified, inflating the variance by a total factor of 6.63. Right, just for this one estimate. So again, we've had this discussion, what should a design effect look like? 2, 3, 4, this is pretty high. But there's a lot of variance inflation that we need to account for in that particular estimate. And the key thing to note here, right, even though that design effect is high, this is still a pretty tight confidence interval. Like if you're trying to make a statement about this overall mean for the entire US population, you know, you have pretty good certainty where it sits. Because that's incorporating this design effect, as we should, right? But we still have a pretty precise estimate, but the NHANES isn't for us. Questions in back?
So with the survey syntax.
Yep.
So I noticed that I changed the number of observations. And
Sure. Change it, right?
So how can we know it?
Well, that's the item missing data problem, right? Some of these variables, you might have missing data for some cases. Some other variables, they might be populated for the full sample, right? That's where we have to think, if you want to do something to address the missing data problem, you might use imputation or some form of prediction of what those missing values should be. But if you're trying, for descriptive estimation purposes, my recommendation would be use all the available information for every variable that you're trying to describe. But for multivariable modeling, right, it's going to be based on complete cases in the data set. What cases have complete data on all the variables of interest? But for descriptive purposes, you should leverage all the information that's available for any one given variable. And so you're going to have a sample size that varies across variables.
I was thinking about usually sample size.
Yeah, there's not going to be one sample size. That's the key thing to note. So in your manuscript, if you were preparing a descriptive table, you might in your table include the unweighted sample size, all your weighted estimates. The key point, remember what we're trying to do. We're trying to compute unbiased estimates of population parameters for all these different things. So if you want to compute that unbiased estimate, you want to use all the information that's available to you to compute it. So you wouldn't want to limit yourself just to the 6,000 cases that have complete data on all these variables, because that would be throwing out 1,100 cases that are contributing to this estimate. You want the best possible descriptive estimate you can compute. If that means reporting a different unweighted sample size, that's fine. You're just saying, I used a particular sample size to compute this unbiased estimate. So the remainder of the lab notes, and you can play around with this, I'm just gonna kind of walk people through this here. The way the lab notes are gonna be structured, you see the pattern is reading in the data, looking at some simple descriptive features of the variables in that data set, like we looked at the crosstab and so forth, and then setting up the design features associated with each of these public use data sets and running a very simple analysis, okay, using that survey type of command. And this first set of lab notes lets you open multiple course data sets. So the NHANES, the NCSR, the HRS down here at the bottom, and then just get a flavor for what how those different design variables are coded, what their names are, and so forth in each of the different data sets. And in the lab notes, I'm going to include the Stata commands to do this kind of stuff and the R commands for those of you who would prefer to use R. So in R, you need to load a handful of libraries, and then you're reading in those same versions of the data sets. I included code here to read in the Stata version of the data set, but there's also R versions of the data up on Canvas if you prefer to go a more direct route. And then you can see kind of corresponding commands in R to replicate what was being done in Stata using the design-based commands. In R, what you have to do, I'll just highlight this real quick. Let's see, I want to find the right here. In R, make this a little bit bigger. So we talked about survey set within Stata for defining the design variables. In R, once you load the survey library, there's a function called survey design. And that creates what's called a survey design object that you input to subsequent analysis commands. Same basic idea here. In that design function, you input the variable containing the strata, the variable containing the PSU ID codes, the variable containing the final weights, the name of your data frame object that you want to use, and this nest says that the PSUs are nested within the strata. That shows that the cluster codes are nested within the stratum codes. That creates this new object called NHANES survey, and then the subsequent analysis commands use that design object as an argument to the analysis command to do the design-based analysis. So in Stata, it's a little bit easier because you can declare those design variables globally and you just have to add SVY. In the R analysis commands, you always have to input that design object that you create here as an argument to a given survey command. But that's what implements the fully design adjusted approach, fully accounting for those design effects. Okay, so I would encourage you, I'm sorry, we're about 15 minutes over, but I would encourage you to play around in Stata or R with this initial set of lab notes, again, just to get a feel for these variables in the data sets leading into our discussions next week. So, George?
The PSUs are not so you don't need to have, in R, you don't need to have that final.
Well, so the danger, a lot of these like if we look back at the Stata crosstab, a lot of these data sets, the PSU codes are going to be coded in the same way across strata. So the danger in R, if you don't declare that nesting, R is going to think that this PSU code 1, all these people are from the same cluster for the sake of variance estimation, which is obviously not what we want to happen. Stata recognizes that directly, but in R, you have to add that nesting option. And there's not going to be a design that we've talked about where nesting isn't true, right? The clusters are sampled from within the strata. We just have to declare that explicitly within R. Otherwise, it interprets everybody with a code of 1 as belonging to the same cluster, which would mess up all of our variance estimates. Okay, any other questions? Yeah, go ahead, sorry.
Nowadays, Stata is the most adjusted software to this kind of analysis, sampling analysis.
In my personal view, Stata has come the farthest along in terms of adapting common analysis procedures to this design-based framework. It's like here I'm in Stata 18.5. If I go into the statistics menu, and then I go down to survey data analysis, look at what's possible in this design-based framework. Simple tables, simple descriptives, linear models, logistic models, ordinal models, categorical, count, fractional, survival analysis, multi-level models, like we're going to talk about, endogenous covariates like structural equation modeling, Heckman selection models, latent class analysis, item response theory models, all of it adjusted for these design features in this kind of integrated environment. R has like a handful of modeling functions within the survey package. SAS has a handful of survey procedures, but no other software provides this diversity of analysis commands that are adapted to this design-based framework.
You answered the other question if I would say about comparing with the SAS.
Yeah, there, I mean, SAS lets you do some things, not even close to the list here.
Yeah.
Yep. So that's the big deal. And so if I'm facing like a typical data analysis problem or something, I'll probably do like the big data management in SAS or in R. If I have to write a program or something, I'll do it in R. But if I just need to do a secondary analysis of a data set like this, it's going to be insane. Like that's pretty much how I operate. That's personal preference, but just given where it is right now. And we'll talk about things that can only be done in R. Like there are some things that have only been programmed in R. We'll talk about that when we get into examples, but I think status for us align is fine. Yep. Okay, other questions? Thanks for staying a little bit longer today. So.
I have a brief question.
Yeah, Sarah, go ahead. Yep.
I mainly, well, you stated, but at work we use SAS, and
Yep.
probably the I'll be using will be in SAS. Is there any way? Is there an easy program out there that converts this to SAS, that would convert data to SAS, or
You're talking about converting static code to SAS?
or basically an easy to figure out how to quickly get this into SAS for the survey data commands, or
Yeah.
just
So the ASDA website, we've shown how to replicate every example in the book using every software that's out there. So if you want to replicate the examples from the book, which we'll start getting into next week, if you want to replicate the examples from the book in SAS, just look at the SAS files on the ASDA website.
Okay. So next week that we'll be following more of the stuff that's replicable. Question about that actually. Maybe you could pull it up quickly, or at least I could stick around a second after. I was having a difficulty because right now I'm going in to the website and I'm seeing the data sets, but I'm not seeing like the examples, or even like for a problem one, the exercises, the actual.
So are you talking about Canvas, or are you talking about the ASDA website?
Website, because
So this is Canvas. So on Canvas, this is not the ASDA website. So this is Canvas for the course.
Yeah.
And in Canvas for the course, you're going to find just the kind of sanitized versions of the data sets that I have prepared for all the examples.
Right.
If you want to go look at all the example code for the analysis replication and everything else, you have to go to the more general website for the book.
Right. Which I had gone there, but maybe I'm just not.
So in the left-hand panel here, like if you're looking for the SAS code, here's all the SAS code.
Okay, overview of the commands, right? So that would make sense.
So you see, like if I click on chapter 5 examples, you see all the SAS code you would use to replicate every example in chapter 5.
Okay. Okay, so basically, if I was looking for homework 1 question.
Well, I mean, for homework 1, you got to do the work yourself, right? So you're not going to find the solutions for homework number 1 anywhere. You got to do that yourself.
Basically, I see what you said. Here's the data set to choose. I see ASDA exercise 5.1. In the book I got, is it actually under 5.7 at the very back, exercise number 1?
Yeah, so you have to go into the book, look at problem 5.1 at the end of chapter 5, and that's asking you to use the ESS data set from the Canvas website.
Okay.
We can, Sarah, we can chat on email or something if you're still having issues, but yeah, you have to download the ESS data and then do some simple descriptives of those data. And if you want to use SAS, you're more than welcome to. So.
Yeah, makes sense. Okay.
Okay. Okay, well, thanks everybody. I think we're all set. So we're gonna see everybody later at Jim's reception tonight. So hopefully you can go. I got my whole family to come, so I'll ride the bus over with you guys, but my family's gonna meet me there, so you can meet the fam. So okay. All right, so have a good rest of the day. We'll see you later.
Thank you.
Yep. Yeah. Yep.
And the target is households, right? It's a households, but they have data individually. So does the target start and the target is to okay, then?
Yeah, I mean, so if you collected data from respondents, I guess the question, like from individual people and not like just household features, you have to say like, again, is the target of inference the population of all households? Or is it the population of all people? Because those are different populations. So if one person is responding on behalf of the household, then everything is probably going to be at the household level. Like if the entire survey is asking them, what are the properties of your household? What are the characteristics of your household? Then you're probably talking about using a household level weight to make household level statements. But if any of those questions are asking about what do you think about this, or what is your own personal income or anything like that, then probably you're talking about like an individual level estimate, and you would need an individual level weight. Yeah, so that's getting it, that's the thing, that's suggesting that if you want to do an analysis like using education and income, that you would need an individual level weight, because education is going to be something that's specific to a person, not a household. So that tells me that you probably need an individual level weight for that kind of analysis. We can chat about it further. Just shoot me an email or something, and we can chat about it offline. A little bit, yeah. I'm gonna go eat lunch. So.
This is like our survey report.
Okay.
So this information, like unweighted woman, we get from the survey data 74,000.
Why is weighted equal to unweighted?
Yeah, this is what I'm talking to you. Because the weight you computed. So this is the column where we get the weighted number of women with computed.
Oh, so you weren't talking about a variance. You were talking about the weight. So you were referring to normalized variance.
No, I was just talking about the normalized rates.
Oh yeah, so weights. Yeah. So this.
You have just spoken about that.
Yeah, this is okay for everything but totals. So if nobody using your data ever wants to compute an estimate of a total, you'll be fine. But as soon as somebody wants to compute a total, this is doing them a disservice.
And then he or she needs to multiply with the population.
If they want to compute a total. Every
other
other statistic, means, proportions, whatever, these will be just fine.
this one, yeah. Thank you.
That's the key. I thought you were saying variances, and I was like, what's the normalized
Just,
variance?
talking about the normal rates.
Yeah.
We were just discussing in the.
That's why I was mishearing. So
Thank you
yeah,
so much.
just don't compute totals using that. That's the problem.
So we can use in the.
You can use it for everything else but totals.
Thank you.
Okay. You have a question? Yep.
It's not a question. I would like it to have an appointment with you
Okay.
in the next days.
Yeah, just
Next week.
shoot me a note. And we'll figure out like the best time that I have an opening or whatever. Shoot me an email and we'll
Okay.
set something up. Yeah.
Okay. Thank you very much.
Yep.